Okay, so what I want to do now for this video is I basically want to go over these methods that we looked at last week and just explain again why these are the correct methods. I wasn't quite happy with the last video that I made. Perhaps it was because I'd meant to do it much earlier in the day, but I had a problem at work that I had to deal with, and so it sort of took my attention. But I want to go back to this and explain why these are kind of the methods that are going to, why these methods make sense in terms of orthogonal projections. So the first thing that I want to go over, just some terminology again. If G is a symmetric positive definite matrix, then we can define an inner product in the following way. So I'm going to use this notation. Also, I'm no longer going to draw arrows over the vectors. With the tildes, that was just getting a little too much, and I was getting more distracted with the arrows than I was the actual presentation of the material. So basically, any lowercase letter you see is going to be a vector. Any uppercase letter you see is going to be a matrix. Okay, so VW in the G inner product is simply AG, whoops, not A, I meant to say G. In a minute, the G will be equal to A, so that's why I did that. GVW, and if I don't put anything there, it just means the standard inner product. Okay, so this is how we define a more general inner product. And as I mentioned in the previous video, anytime we have an inner product in Euclidean space, it can always be given in this form right here, where G is a symmetric positive definite matrix. Okay, so that's one thing that I want to remind you of. Another thing that I want to remind you of is the following. Anytime you want to do something like this, so minimize, I almost wrote min. Anytime you want to do something like minimize this for y in some subspace, I'm just going to call it S. S is some subspace. Anytime you want to minimize this, an expression of this form, z minus y, relative to some norm. Okay, so anytime you want to minimize this, the solution which I'm going to call y tilde, is the projection of Z onto the subspace S. And my phone is making noise, so let me just mute it. Okay. And remember then what this means, like another way to say this, is that the vector Z minus Y is orthogonal to every vector in S. So another way to say this is that the vector Z minus Y tilde is orthogonal to Z minus Y tilde, the dot product of Z minus Y tilde, and V is equal to 0 for all V in the subspace S. Okay, and this inner product here is not necessarily just the standard inner product. It could be, we could measure this minimization could be in terms of the norm induced by the G inner product, and then the orthogonality would be the orthogonality that is induced by the G inner product. Okay, so I've said this before, but let me just remind you. The norm of a vector relative to the inner product induced by G is simply this is just the standard thing, is just that. Or if you want to write it in terms of, the normal, the standard Euclidean inner product, this would just be GV v like that. Okay, again, these are just standard linear algebra constructions. It might be a little more abstract in general than what you remember from your linear algebra class, or in a certain sense it might be, since we're talking about defining the inner product specifically with a matrix, it might be less general than what you're used to. Both less general in some senses and more general in other senses, right there in the optimal space for being confusing. Okay, so I want to explain how we can see both of these methods as projection methods. I want to look at how we can see both of these methods as projection methods. That is, why this gives us, why the solution here is a natural result of a projection method. Okay, so I'm going to start with number one here. And so let's say we have a starting vector x naught, and we want to minimize delta. Okay, we're going to restrict delta to our subspace K. What is K? We haven't determined how to decide that yet. I haven't told you how we're going to decide K, but let's imagine we have some K. And we want to minimize this. And what we want to do is we want to minimize the error between the actual solution and our updated solution, which is going to be x naught plus delta. And we want to do this relative to the norm induced by the matrix A. Okay, so remember in this case right here, A needs to be a symmetric positive definite matrix. So let me just say here, for this method to make sense, A is symmetric, positive, definite. So then we can define the inner product. Okay, and we'll talk more about this in just a minute. Okay, so this is a very reasonable thing to do. This is the actual guess. This is the updated guess. And we want to find the updated guess that's going to minimize the error between the actual guess and the updated guess. And doing it with the A inner product, or doing it with the norm induced by the A inner product, seems reasonable because that's what we're dealing with here. Okay, so notice that we can just rewrite this very simply as we want to minimize delta in K. I'm just going to do associativity here. X star minus x naught minus delta. Okay, so what this means is the solution delta tilde, if I call it the solution this delta tilde, it is the projection of x star minus x, x star minus x naught. I need to write an A here. It's a projection of x star minus x onto K relative, or I'll say with respect to WRT, the A inner product. Okay. So in other words, it means that x star minus x naught minus delta is orthogonal to K in the A inner product. So in other words, we need to have the residual vector, which is x star minus x naught minus delta, to be equal to 0 for all V in K. And again, this is relative to the A inner product. Okay, well, if we just write out what this means, what is the definition of this? Well, it's A times the left component, and then the right component stays the same. A is symmetric, so we could also put it on the right component. So we want A times x star minus x naught minus delta tilde, comma V to be equal to 0. Okay, well, let's start unpacking what this is. So AX star is a solution, so AX star is equal to B. AX naught, what is AX naught? That's just the previous thing. So R naught is equal to B minus AX naught. AX star is equal to B, so AX star minus AX naught is just equal to R naught. And so this right here, we can rewrite as R naught minus A delta. So in other words, we want R naught minus A delta to be orthogonal to, we want the inner product of, so let me say here, for all V in K, we want this expression to be equal to 0. We want this expression to be true for all V in K. But now this is just the standard inner product. So now what this means is it means that R naught minus A delta is orthogonal to K, but in the standard inner product. But that's exactly how we pick delta here, so that R naught minus A delta is orthogonal to K in the standard inner product. Okay. Now, there are other ways that we can think about this. There are other ways that we can think about this. Another way that we could write this would be the following. We want to minimize the delta in K. Okay, what is x star minus x naught? Well, this is just the error from the previous step. So let's call that E0. E0 minus delta, the A vector. In the A norm. Okay, so now what this means is delta is equal to the projection of E naught onto the subspace K with respect to the A inner product. That's what that means. Okay, so we can see delta as being the projection of the error onto this subspace. Okay, and the idea is that these subspaces are going to grow. So each time we're going to get a better and better approximation to the error. And if we have a better and better approximation to the error, that means we have a better and better approximation to the actual answer, right? If you know this is your guess and you know the error exactly, then the true thing is just going to be the guess plus the error. Okay, so if the error is smaller, then your guess plus the error is going to be closer to the actual thing. Again, what this means is A times E naught minus delta, do that inner product with V, this is equal to 0 for all V in K. Okay, but notice how we can write this. A E naught, well, what is E naught? Again, E naught is x star minus x, and so this is just the residual vector. A E naught is just ax star minus ax naught. So again, write down what E naught is. E naught is x star minus x naught. So A applied to E naught is ax star minus ax naught, but B is equal to ax star. So this is just going to be the residual vector R0 minus A delta V, and this is going to be equal to 0. Okay, so in other words, what we're saying now, we can see the way that we can conceptualize this. We can either think about delta as being the projection of E naught onto K with respect to the A norm, or we can say that A delta is the projection of the residual vector R naught onto the space K. Because again, if this is equal to 0 for all values of V, if you have the solution, let me write this with the solution. If delta tilde is the solution to this, then it means delta tilde minimizes R naught minus A delta tilde relative to the standard 2 norm, the standard inner product. If there's a 2 there, it just means the standard inner product. Okay, so this tells us why this process right here is a reasonable one, and it minimizes a certain error. In particular, it minimizes the error between the actual solution and the updated solution relative to the norm induced by the A inner product if our search space here is K. Okay, so let's do something similar. I'm going to put my chalk down so I don't drop it and break it. Let's do something similar but for the second method. Okay, so let's move on to number 2 now. Now for number 2 to make sense, A doesn't need to have any properties. A just needs to be a matrix. So I guess that's one property it needs to have. It needs to be an n by n matrix too for this to really make sense. Okay, so again, what we're trying to do is we want to minimize something. Previously we were minimizing the error. We could also minimize the residual. So we have to pick what we're minimizing and how we're measuring that error. So for this one, we're going to minimize the residual, and we want to do it just with respect to the standard inner product. So we want to do something like minimize delta in K, not A, the residual B, okay, that's the actual solution, minus the updated solution. Sorry, B isn't the solution, B is the right-hand side of the problem, x naught plus delta. And again, we're doing this in the standard 2 norm. Now we can rewrite this in the following way. So we're going to have B minus AX naught. But what is B minus AX naught? That's just R naught. B minus AX naught is R naught. So this is going to be R naught minus A times delta. Okay, but delta is in K. So what I'm going to do here is for item number 2 here, V is an n by m matrix whose columns span K. So then as delta runs through K, we can write delta, we can write that as V times Y. Okay, and now as Y runs through Rm, V times Y is going to run through K, and then I still have, and remember it's A times delta. So it's going to be A times delta like that, or A times V like that, and this is going to be Y in Rm. Okay, and again, the whole reason is as Y runs through Rm, V times Y, you get all of the linear combinations of the columns of V, but the space K is spanned by the columns of V. That's how we were defining V. So as Y runs through Rm, Vy runs through the space K. Okay, so now what we're saying is the solution Y tilde is the projection of R naught onto the space spanned by the columns of A times V. Or actually, this notation here typically means the column space of AV. So we could just say the solution Y tilde is the projection of R naught onto the column space of AV. Okay. Or the column spanned by, or the space spanned by the columns of A times V. But those are both the same thing. Okay. So what does this tell us then? Well, first I want to figure out what the space spanned by the columns of AV is. But what this tells us is the following. It tells us that R naught, or maybe not first I want to figure out what that is. I want to say what this is. Okay. R naught minus AV Y tilde. The inner product with Z is equal to 0 for all Z in the column space AV. Okay, well, let's think about what the column space is. Let's think about what the column space of A times V is. So it's going to be the set of all vectors of the form A, V, let me say A, V, U, AVU, where U is an Rn. That's just the definition of the column space. All of the linear combinations of the columns. Okay, but what is V times U? As U runs through Rn, V times U runs through the space K. So this is going to be equal to AV as V runs through the vector space K. But this is exactly equal to A times K. What does this mean by definition? It just means you take every vector in K, you do A times V, and that's going to be, all of the elements of this set A times K. Okay, so in other words, this space is equal to A times K. All right, so the column space of A times V is equal to A times K. So this is equal to A times K. So now what we're wanting, I'm going to have to erase these here. So now we have our solution y tilde. If we set delta tilde is equal to V y tilde, then we can just write this as R naught minus A delta tilde comma V is equal to 0 for all, or let me do Z because that's what I have here, is equal to 0 for all Z in AK. In other words, we want R naught minus A delta tilde to be orthogonal to AK, which is exactly this condition here. Okay, so both of these methods, 1 and 2, come from minimizing an error relative to a certain norm. This method 1 comes from minimizing the error, the actual error between the current solution, or between the updated solution and the actual solution in the A inner product. And here we are minimizing the residual where we're computing it with the updated value here in the standard inner product, or the standard norm. So here we're measuring the error relative to the A norm. Here we're measuring the residual relative to the standard norm. And both of those, are intuitively reasonable goals or reasonable measurements to have. And then once you have those measurements, you see that it's, equivalent to solving these problems here. Okay, last thing that I want to mention about this method, if we go back and rewrite this as A delta, okay, what we're saying then, I want to say something similar to what I said on the first one, is this is the projection, so A delta, let me change this back to delta and V, or delta and K. A delta is the projection of R naught onto the subspace K. Okay, let me just check my notes to see if that is in fact all that I wanted to say here. Okay. Yes. Okay. One other thing. So if R tilde is equal to B minus AX tilde, okay, let's unpack this a little bit. R tilde is going to be equal to B minus A. What is X tilde? X tilde is simply X naught plus our delta tilde. That's what we're calling the solution to the minimization problem. And then how can we write this? Well, B minus AX naught, that's R naught. And then A delta naught, A delta, we can just write this as A delta tilde. Okay, but what is A delta? It's the projection of R naught onto the subspace K. So I can write this as the identity operator minus the projection onto the subspace K R0 like this. Okay, so that is another way that we can think about this, and we can use this to come up with formulas and error estimates and things like that. Okay, so that's it for this video. I just wanted to start week 6 with a slightly updated, and I hope if you didn't like the video, or the video from Friday was a little too hard to understand, or maybe lacked a cohesive framework, this is the updated video. So sorry about that. Like I said, I made the video on Friday at 5 or 6 o'clock. I was, my nerves were frayed by then, and though I had my lecture planned out in the way that I wanted to give it, I just felt that there were times when I was not doing it the way that I wanted.